energy of the reactant as the reaction is proceeding. Anthony tells me, you start at this level, you end up at this level. What happens in between? Kind of just told you. If this is the energy required to reach that transition state, it has to come from someplace, folks. I know you've been taught. No, it lowers the activation energy. Not really. It provides the activation energy, which means what is happening to the energy. Yeah, Anthony, got it. As a matter of fact, it should be exactly this low right here. Where is the enzyme most stable? What do you got, see? When it's bound to the transition state, because it's providing the energy that's required for these guys to come to some unstable intermediate process right here that allows them now, guys, if I were to look at any given reaction and look at the reactants/products and see that it is in the transition state, what dictates whether it goes that way or this way? Do you all recall talking about from the transition state? I can't stay there. I can go on to forming products or I can go back to forming reactants. What determines which way I go? Concentration of what?
Either.
Enzyme?
No.
You sure?
Products or reactants.
The ratio of products to reactants relative to the equilibrium constant. Oh yes. So whether I have an enzyme present or not, once I'm here, I can go this way or this way as that transition state. Which way I go depends upon how many more of these things are than this relative to the equilibrium constant or vice versa. Capiche? So the equilibrium constant is important to me. The energy is recent of the process is concerned. Which way I go, so what's the enzyme have to do with that? Absolutely nothing. Whether I go this way or that way, the enzyme doesn't give a crap whatsoever. It just says I can get you to the transition state more easily. Why? Because I become more stable when I do that. How does an enzyme do this? What can an enzyme do to make a transition state form more easily? Does anybody remember any specific catalysts from organic chemistry? I'm only asking about organic chemistry because I know that's the one class that all of you have taken where you talk specifically about this reaction is catalyzed by this kind of catalyst, and this kind of reaction is catalyzed by this kind of catalyst. Does anybody remember any reactions in organic chemistry? Yeah, Katie, what do you got? Platinum as a catalyst, right? Remember what kind of reactions it was involved as a catalyst?
Something with hydrogen.
Hydrogen sounds like a good answer right there. Yeah, I know part of your brain is saying, but Franz, that was organic chemistry. It doesn't. Wait a minute, hydrogen interacts with things in us when we are saturating. When I'm breaking down fat, forget fatty acids. When I'm doing the Krebs cycle, am I making alkenes? Okay, who's studied the Krebs cycle before? I'm serious. If you've had a test that involved questions and the Krebs cycle, please raise your hands right now. And you don't know whether any alkenes are formed or not? Why is that? Do you think that will fly in this class? No, it will not fly even for a second. You have to know the reactants of the yes. And when you see it presented the right way, it's easy, right? You will, in the future, be sending me text messages like I got this morning from a guy who's in med school at where is it? Someplace in Detroit, or outside Detroit. I can't remember the name of the med school that he's in. Got a scholarship there. He said, I've got the phone with me, quote, Westchester University prepared me so well for my master's and for medical school, all right? Not doing as well in anatomy as he wants to be doing. He's getting like a B plus in that. He's kicking butt in biochemistry because he sat through this crap right here. He's learned all these details, all the fine stuff about this, so they can go way past that in more advanced classes and say, oh, I know the simple stuff right this very second. The enzymes that we're talking about, the catalysts that we're talking about, in organic chemistry and in biochemistry, they're going to be the same kind of thing. Now, we don't use platinum. Does anybody know what platinum does to hydrogen in the process of addition to an alkene, for example?
Doesn't platinum hold two hydrogen atoms for the alkene group to attach to it to make an alkyne
Now, what would the transition state be there? Maybe some of you remember. What do I need to do to hydrogen to make it addable to an alkene? You may recall nickel does this. I can increase the temperature, that's one thing, all right? What does it do?
I didn't understand in class. So it was like, I remember it.
They look on your face like, yeah, I should have, but I got away with it, so I just kept right on going right
Yes,
now.
I just knew it was pressure.
What do you think it could do? Your pressure is going to be a matter of making more molecules slam into each other. I don't need platinum for that, I just need to increase pressure. But without the platinum, it doesn't happen all that easily. What do you guys think the platinum is doing to make it want to react with an alkene? What could it be doing to an alkene? See, I don't like platinum because it's good at what it does, but it's not anywhere near as good as enzymes like fumarase or enzymes like enolase will act in glycolysis in the Krebs cycle to make alkenes form in the first place, and then other reactions that actually get those guys to keep on reacting. They are much, 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 much better at that because instead of just providing a surface where the hydrogens or the carbon-carbon double bond could stack and kind of get stretched, they can do other things. They can actually orient molecules so that they can get both the right kinds of molecules summing into each other as the right things are being stretched. What enzymes are going to be doing is basically providing that surface. But they're also, does anybody remember specifically how you hydrate an alkene? Because this reaction absolutely does happen in both glycolysis and the Krebs cycle. Sorry, not idiot. Mike is outside. Mike ready? Anybody know? Longer. Maybe you remember acid catalysts? What's an acid catalyst going to be doing? Oh, please, after this class, you guys have to know what an acid catalyst is going to be doing. Acid, you know, it acid catalyses things. If I'm going to act as an acid to catalyze the breaking of these two guys right here, what's your name? Nishal? Bishal?
Yeah.
Are you raising your hand or?
Kinda.
What? In a half-assed way.
Yeah. Then to make the alkene electrophile, the water can.
Make it an electrophile.
Yeah.
Electrophile would have what kind of charge?
Positive.
How would an acid make an alkene positively
Never mind.
charged? No, don't do that! Guys! But Frost, when people ask us questions and they say the words back to us in a bad way, we know we made a mistake. Yeah, in weak classes that might be. Don't do that. Is an acid going to make something that it interacts with more positive?
No.
What do acids do, folks? They donate hydrogen
Protons.
ions. If I give you a proton, does that make you more positive? Yes, as a matter of fact. So, Bishal, were you wrong about that?
No.
No, so why did you that? Actually, Frost, the reason I did it because I was amazed that I might actually know what I was talking about. And isn't that amazing? No, proton, I'm a proton donor. I give you a proton, makes it more likely to react with what part of an oxygen molecule? And we're talking about the hydrolysis or the hydration of an alkene. If I give my proton to one of these two carbons right here, that makes it more positive? Yes. All right? Actually, if I give it to you, what does that H plus do to the double bond? Yeah, what do you got, Noni? It's going to pull one of those pairs of electrons to it, making this guy the carbocation, correct? And do you see the Shaw and everybody else? Oh, that makes it react much more easily. Does this carbon as an alkene want to react with an oxygen? Or hydrogen? No. But if I jam a proton on this guy right here, making this the carbocation, what part of the water molecule will it react with? Sorry, will Abigail react with as that carbon? The oxygen part. Ooh, but that has too many bonds. So what has to happen to the water molecule? Has to give up of what? Hydrogen ion. Of course it does. Why? So I can go to the next alkene. And I go to the next alkene. It gives me my proton back, and I go to this carbon right here. I go to this carbon right here. Oh, yeah, that's right. They don't get used up. They do get used. Why did you do that in the first place? Because I'm an acid. I want to give my proton to something, even if it doesn't want it. The transition state in this case is the carbocation. The transition state in your case, as Katie and Colin, is one of those hydrogens being more of a hydride, the other one being more of a proton, or the carbons involved in a double bond. One of them being more of a carbocation, one of them being more carbanion, by the platinum forcing that pair of electrons one way or the other. The beauty of an enzyme is that I could do that while other guys are also stabilizing this positively charged carbocation and stretching the bond to the point where, hey, you don't want to break it in the first place, because you guys recall that alkenes are kind of short bonds, right? And then an alkane is going to be formed more easily, or an alcohol is going to be formed more easily. You can stretch one of those bonds, pull it one way or the other, stabilize this guy right here. Hey, that's exactly what a bunch of different catalysts did, but they all did it separately. Enzymes can do all these things because they have the functional groups or the prosthetic groups that allow all these processes to take place. Why does an enzyme want to do this? Why would I want to catalyze a reaction the way I just kind of described it right there, with all these various things happening?
Because the enzyme is in its lowest energy
Because
state.
I get to a lower energy state. I'm sitting here, it's like, gosh, you know what would really be cool? If there'd be a carbon coming in and another carbon over here that has this kind of arrangement right here, so that my active group, my side chain, and these side chains over here, and all these other side chains, we go through all these conformational changes to bind to this, stretch this bond, donate a proton, stabilize this carbocation. We're all happy like this. So why don't we stay that way? Because these guys aren't happy this way. They're the most unstable under those conditions. So they're either going to go on to form products or back to forming reactions, but they're not going to stay like that. If I can come up with a molecule that sort of looks like these guys in the transition state, but is not unstable, what do I have? If I can make a molecule that looks enough like this transition state right here that I can bind to it, you got,
Intermediate?
huh?
Intermediate?
No. It would be an intermediate if it's not very stable. But if I've got a molecule that kind of looks like this guy right here has a positive,
You got a competitive inhibitor.
I got a poison, right? You say, oh, is that what some drug companies are? You bet that's what they're trying to come up with, because when the enzyme binds to it, it says, nope, I'm done. I'm happy right now. I've reached my lowest energy state. So your job as PPD guys, as chemists and biologists working for drug companies is to come up with things that either look like the transition state or look like an allosteric effector or inhibitor or activator, depending on whether you're going to turn on or turn off certain enzymes, because you need both things to happen under various circumstances, which we will not spend much time talking about, okay? Anyhow, what catalysts are, and this is something I really want you to remember, they lower the activation energy, and I put an asterisk by that, say, yeah, you know, actually what they really do is provide the activation energy by making the transition state more easily attained, all right? Making it more stable. They hasten the attainment of equilibrium, but they do not alter the equilibrium. They are not used up, but they are used. They are reacting and changing, at least conformationally, in some cases quite substantially. As Colin said before class, he said, yes, they may change, and he said the word drastically or not drastically. I can't tell you whether it's going to be drastic or not, but there's going to be some conformational change. My key is not a key. My key is something that is changing as it interacts with this lot, which is also undergoing changes, reaching the transition state, okay? The way we go about measuring these kinds of things, all right? This is the picture I showed you before, all right? Again, the more accurate model for what an enzyme is doing is what's referred to as the induced fit model, and everybody see what's wrong with this picture as what's supposed to be an induced fit. Just give me 1 second, folks. This right here would be a lock and a key type model. You can see right here, hey, these guys don't want to change. They want to stay together like this. This is crap, all right? I don't know which is locky. I don't really care about that part. I do not like this because there's no driving force for these guys to separate from each other. That's kind of true up here too, right? What's wrong with this model of an induced fit interaction between some enzyme and its overall reactant or product?
The enzyme's already in shape that needs to take in.
That's close enough, but it's changing. What would make this more accurate, Melanie, what? The substrate, the reactant or product, has to become a lot more uncomfortable. It doesn't look like that here, does it? Now, this is from your textbook. Doesn't make a difference which version you got, short or long, doesn't make a difference. Not really very accurate. Both the reactant products and the enzyme are undergoing changes. The enzyme is becoming more stable. The reactant/products are becoming less stable to reach that transition state. All right? when we come in on Monday, all right, we're going to go very quickly through a very brief derivation of the Michaelis-Menten equation, and more importantly, a little bit of how we could go about using it. This is questions on the quiz. What you are looking at on those quizzes is not just regurgitating crap like Km is the substrate concentration 1/2 of Vmax or 1/2 of Vmax. What it tells me about what an enzyme likes to interact with or can't interact with all that well, all right? When most of you have talked about this, if you did it all, in cell phys, you memorize Km, 1/2 of Vmax. No. Substrate concentration, 1/2 of Vmax. Why is it that? I'll show you very quickly, according to the Michaelis-Menten equation. The problem with the Michaelis-Menten equation is you can't always reach Vmax when you set up an experiment that way. So it's easier to use the inverse of that, which is what the Lineweaver-Burke equation is all about. And then you can calculate more easily. So look at both of these equations and say, oh yes, so if you give me a Lineweaver-Burke plot, I can come up with some possible parameters, recognizing, as I said, that the active site concentration for any comparison of enzymes or enzymes under different conditions is going to be equal to 1. Vmax becomes your Kcat. Kcat tells me about what an enzyme wants to do. The comparison between Kcat and Km gives me how well an enzyme can go about doing its job. Right? Just look at the equations first of all. Try and answer some of the questions before you come walking in on Monday. I hope they'll give you all the rest of the answers that you don't have at that time. Okay?